Hello everybody, I'm Peter Denning, hosting you in the Harnessing AI course series. So today we're going to have a conversation about natural language processing. This is one of the earliest goals of artificial intelligence, was to see if it was possible to have computers that could do things in language with us. So for example, could they talk with us? And then, as you know from the Turing test, behind that is if the computer could talk with us, could it convince us in the conversation that it was intelligent? And then there were other aspirations, like could we translate between languages? Could we translate one language to another? Could we do that in real time so that you could take some kind of language translator with you to a foreign country and speak effectively in their language? Could you generate speech by taking output from a computer and turning it in, it sound like somebody reading it or speaking it? And all of these things sounded like wonderful goals, but they turned out to be extremely hard to accomplish. And we've made, in whatever it is, 50 years now, we've made significant progress with these things. There's still a lot to go. So today we have Professor Neil Rowe here to talk about these issues and give you a sense of the complexity of this field and what's been accomplished and where we're still looking for more accomplishments. So we've already introduced Neil earlier, so I don't need to reintroduce him, and I just welcome him. Please give him a welcome. And Neil, thank you.
Okay, great. So as Peter says, there's been a whole long history of trying to do natural language processing in AI. And you know, part of the reason is that, you know, people would feel really confident, really trusting of AI if it could talk to them, right? So it has to do with the trustworthy aspect of AI to a large extent. But also, since people interact by speaking and also writing, you know, that would be a good way for AI to communicate with us, since we're very comfortable with those forms of communication. Other methods of communication are possible, like what animals do, but those are not as central to the human experience. So it's always been a goal to try to do something with natural language and AI. And there have been challenges, but a lot has been accomplished over the years. So the idea is that you know, we want to keep working on this in different ways. Peter mentioned some of the key things, like communicating with automated systems, particularly in time-critical situations. It's often easier to say something rather than to write something down or enter it into a computer. So that's an important extra channel that could occur, for instance, for pilots of an aircraft who don't have a lot of time to be using displays if in crisis situations. Also, you know, categorizing documents has always been a goal of a lot of this processing, natural language processing, because we'd like to be able to at least make sense of all the words that are coming in around the world and try to figure out what's important, stuff like that. And we have made slow progress on that over the years. Also, key concepts like being able to look things up. Google tries to look things up just by keywords, but Google doesn't really understand what the words are trying to say. It doesn't figure out the sense of words, for instance. It just uses the literal words. So it'd be nice if we could have things like Super Google that would be better able to find us things on the internet, information on the internet. That's particularly important for intelligence agencies that are always scanning for information that could be relevant to them. So you can do that, it's just that you can't do it as fast as what Google does. So if you're willing to put in some extra time, you can get that capability today. And then finally, translating has become a really important thing, particularly in recent years with better translation systems. So speech understanding is one of the main areas. These are sort of like the main areas that there are in AI work on natural language. So certainly we'd like to be able to speak in speech, but of course a lot of the world's information is written down. And so we also want to do some text analysis and text recognition. And that's an easier task than speech recognition, as I'll explain in a moment. So that's the one that's been tackled first, the text understanding problem. To go with that, of course, you got to know what all the words are of a language. whether it's speech or whether it's written stuff, you've got to have a dictionary, basically. A typical English dictionary for useful functioning individuals is like 40,000 words. So compared to the size of AI systems we got today, 40,000 words isn't too bad. Morphology is the endings on words, so you got to understand how different words have different endings that indicate something. And then more complicatedly is the grammar. You've got to know the grammar of a language if you're going to expect to be able to understand that. Now Google doesn't bother with that. Google just looks for little strings of words, but you can definitely do better at understanding things if you know the grammar, which is the set of rules for how words are put together to form a meaning of a sentence. But besides grammar, there's also another thing which is called semantics, which includes a lot of different stuff. Given that you know how the words go together in a sentence, what are they trying to say? And semantics is an interesting issue. It relates to other areas of AI because you have to have a theory of knowledge in order to understand the semantics of a sentence. You have to have basically an idea what all the entities being talked about are and how they relate to one another. And you've got to be able to map a sentence that you see onto that understanding that you have already. And that's one of the harder areas of natural language processing. But it does relate to the rest of AI. So as the rest of AI has been making progress, we're making progress on semantics too. Discourse analysis is a term for looking at larger structures than just sentences. You can make a lot of progress with just AI being able to interpret individual sentences, but to understand paragraphs or stories or things like that, you're going to need some additional techniques which fall into that. And then, as I say, there's a big amount of work now on translation, which we'll talk about in a moment. So speech understanding, you've probably seen all these systems. There's been a lot of progress in the last 20 years. And mainly that progress is due to just the speed of systems. It hasn't been due to any new algorithms or any new methods or any breakthroughs in AI. It's just been that finally computers have gotten to the point where we can, they keep up with what people are doing. One of the problems with having a conversation is you have a certain minimum amount of time you're able to wait between when people are talking in order to keep up the conversation. So until we got to the point where AI systems could respond within a second or so to a speech that they heard, they weren't very useful. We had systems back in the 70s that were pretty good, but they would take several minutes to respond to one short utterance and figure out what it was saying. And that wasn't very good. So eventually we got to the point where things are going much faster. Of course, it's easier if there's a limited number of things a person could say that the AI system has to distinguish. So for instance, if you use just the digits, if somebody speaks the names of digits into a system, usually that's pretty good because there are only 10 things to distinguish and they sound somewhat different from one another in English, and you can usually do pretty good with that. But so it's really a key, the size of the vocabulary is really a key issue with natural language processing. If you have an unlimited vocabulary, it's much harder to do speech understanding. So that's why all these online systems, that use speech understanding limit you to a certain number of answers. Anyway, so there's a database of pronunciations of words you're going to have to do to, so you're going to have to be able to handle all the different ways people pronounce things in different dialects. And that's particularly a problem with English because English is widely used all around the world and everybody speaks with a different accent, right? So if you're going to have a general purpose English understander, it's actually quite tricky to adjust to things. Certainly you can do better with processing if you know the usual sequences of words, so that's grammar, right? Knowing grammar, and also if training for a particular speaker, you learn the way they make their particular sounds. So here's an example of speech just to show you how hard it is. So this is the word phonetician, and what you usually do in analyzing speech is you break things down into frequencies. You do a frequency spectrogram. So what you're seeing over a period of 1 second, the frequency energy, the energy of the different frequencies that people were uttering, the person was uttering here, running from about 1,000 hertz, which means 1,000 cycles per second, to about 8,000 cycles per second. And you know right away that some of these periods are pretty noisy. Like this here is what electrical engineers would call white noise. That's the F sound in phonetician. And see, there isn't very much to distinguish that. And you compare it to some of the other the SH sound, the shun, which is that big black area on the far right there, you can see that there's quite a lot of stuff here that that's really hard to distinguish. On the other hand, there are things like here, these are the vowels that the first vowel would be O, and so this is actually the O sound here. And you see it does have some particular peaks here. The darkness indicates the amount of sound energy there. And so you can make a map to where these peaks are and be able to recognize vowels that way. Of course, everybody pronounces things a little bit differently, but mainly it's based on the frequencies are based on your vocal tract, and everybody has a somewhat similar vocal tract. So they're usually you can pick out vowels pretty well. But the consonants are harder, and particularly the noisy sounds like F and SH are going to be really hard. So when people started trying to do AI for speech understanding, they had to confront the fact they've got a very noisy input here, that they've got to interpret stuff. Of course, what people do is they look at the context. They know that there's only a certain number of words, like 40,000 words in English, and all they have to do is recognize one of those, which is a lot less than the total sequences of sounds you could make if you had 10 sounds in a row there. The sounds, by the way, are called phonemes, so there's a whole thing about phoneticians and phonetics that you have to use to do AI on speech understanding. So it was a hard challenge, and oh, by the way, these funny things, you notice the slats there in the vertical bars there? That's your glottis there, you're vibrating. That's the voice box making noise. It basically creates these sounds by flapping some tissue there against the sides of your mouth, and that sets in motion the other parts of your vocal tract, much like the way an organ pipe is excited by some noise at the bottom, created by the bottom. So you see that's a pretty low frequency, that flapping there, and but it sets in motion all these much higher frequencies. Okay, so there's two types of natural language processing. There's the shallow processing and the deeper processing. And so most of what's going on today with systems is what I'd call shallow processing, where you basically don't try to understand what's being said, you just try to recognize. And so, for instance, on an online telephone system that's taking in your credit card number, for instance, all it has to do is recognize those 10 sounds, doesn't have to recognize grammar rules or anything like that. And so you can get quite far with just shallow processing in many types of things. And there are many different ways people are doing shallow processing right now. So for instance, you might want to recognize spoken words from a small number of possibilities, find text matching some keywords. So for instance, intelligence agencies are looking for the word jihad, for instance, in Arabic text, and they're looking for particular words that might suggest terrorist groups so they can get early warning of what terrorist groups are up to. So you can just scan them. Of course, terrorist groups are not shy about advertising their goals online, by the way. Even relatively primitive countries, the terrorist groups know that the best way to recruit people is to put something on a web page. And so there's often quite a lot of information that you can process. It's already in written form that will give you lots of useful intelligence these days. You may want to classify text. For instance, spam is a classic example. There are certain words that indicate spam. Anything involving urgency, like buy now or things like that, or advertisements about how cheap they are, inexpensive, how much money you save, stuff like that. So the words related to those types of pleas, the spammers can't really avoid those. They know that those are the words that get people to buy stuff, and so they use those. So similarly, there are lots of other ways that people have applied classification based on a list of words. For instance, classifying an author. You can classify emotions. For instance, one thing that's interesting is try to detect if somebody who wrote a blog entry is angry or not. And deception, I'll show you an example in a moment. Other thing you can try to do in shallow processing, learn which words go together. So you can maybe build up knowledge of the technical terms in a particular area. So even if you don't know anything about some narrow particular type of medicine, for instance, you could maybe look at research reports on that and find what terms are co-occurring there, and you can build up at least a list of terms in that area, even if nobody has ever made that list of terms before. So the hope is that some of that co-occurrence stuff would allow you to discover stuff, not just model what people are doing already, but discover things in AI. Then translation, you may be able to do translation. You've probably seen Google Translate, which I've used quite a bit in lots of different things there. And so Google Translate basically looks for matching pairs of translations. So it finds an English version and a foreign version, and it figures out which pairs of words or which triples of words or quadruples of words match to which other ones in the document. And then when it sees those, it can use those as a basis for a new translation. And so it's a relatively simple approach, but it's worked better than some of the more fancy AI techniques that people have tried on that. And so I'm generally a fan of Google Translate. However, it has a lot of problems with Arabic and even more with Chinese, because there are a lot of differences with those particular languages. But it's great on the European languages. Yeah, here was a paper from a number of years ago where they were looking for evidence of deception in text. And often people aren't aware that they're giving word clues, that they are being deceptive. And so they did a study. They had some texts that were deceptive and some that were non-deceptive. And they found out that, for instance, if there's less use of the words I, we, and my, that might indicate somebody's deceptive. If they're using less of the words except, unless, without, those tend to mean that there's some doubt in the speaker's mind. And if you want to deceive someone, you don't want to give them any doubt as to what you're claiming, so you try to avoid words like that. And then there was increased use of words like hate, dislike, ignore, strong emotion words, and increased use of move, go, carry, and take. Now, the exact psychological theory of why these things are evidence of deception, we can argue about. We're not really sure. But the fact is, you can just take some deceptive texts and some non-deceptive deceptive texts that you know in advance to be either deceptive or not, and you can train on those. And relatively simple approach is easy to implement, and it can lead to lots of useful stuff. At least give you a clue when somebody is deceiving you. So here's an example of processing that you could do if you've got simple sentences. I had a project a number of years ago where I was looking at descriptions of radar signals at Point Mugu, the Navy Air Warfare Center. And so they have experts that around the world that have listened and analyzed these signals and done the frequency analysis and stuff like that. And so they wrote up descriptions in English of what was different about each signal, what was distinctive about each signal. And intelligence analysts who come across the signal in the future can use that. But one of the things they wanted to do was put it all in a table, and they didn't have any good way to do it manually. So I built a system for them that would go through the natural language and extract out key stuff. And usually there's a bunch of things that are pretty easy to notice as being specialized, like something like this we can see as a latitude and longitude, right? And 1300, that's probably a time of the day, right? And so once you see those things, they're pretty easy to pick out what they're talking about. And if all you want to do is put data in a table, you may not have to understand the whole sentence. You may be able to pull out stuff. So in other words, 50 knots, that's a specialized speed term here. So it's telling something that has a speed, and you can look in the sentence and figure out it's probably the powerboat that has a speed, because boats have a speed, they're vehicles, right? And using that, some simple methods with shallow processing, you can pick out a lot of the meaning of the sentence there. And once you do that, you can start to figure out things like maybe associations, like between Chinese and powerboat and between powerboat and leaking. You may get a rudimentary understanding of the sentence. However, what I really like to do is deeper processing, and in deeper processing you would have to actually do a parse of the sentence and start to do semantic interpretation, and that's going to take longer. Okay, so here's an example of Google Translate, how it builds up translations. So network security, you translated into Spanish here, and software suite. So if you put those two things together, you can get a translation by just appending the first bunch of words to the second bunch of words. Not perfect. Sometimes you can't just put them one after another, but it works pretty good for giving you at least a decent translation of a lot of stuff. And that's helpful when you're trying to translate from a foreign language to English. There's usually a good English speaker can figure out, even if it isn't worded perfectly, what the general meaning was. You can also include verbs here, like purchase our new software, and then you can combine 3 and 4 then, and we get a longer sentence. So using these pieces that we know to translate, we can build up a larger and larger translation from that. And this is the technique that's turned out to work really well for translation these days. Of course, Google has access to a huge library of text all around the world. They have an unfair advantage over lots of other businesses. And so usually you can find a translation of something. There's lots of examples of reports that are required by law to be translated in other languages. So all Google has to do is find a pair of a document and its translation in another language, and they can take advantage of that and do this kind of analysis to build up translations. Okay, so deeper natural language understanding, not to be confused with deep learning, which you probably heard about a few times already, requires a full parse and full semantic interpretation. So I'll explain what parses are and what semantic interpretation is. Also may require analysis of goals. Oftentimes when people utter things, they're trying to achieve something by saying those words. And so you got to have some idea of maybe the goals behind what people are saying in order to understand what they said in many cases. As I say, the speech is really noisy. There's a lot of noise in the speech. But even in written text, there's a lot of confusion because there are a lot of different word meanings in English. A typical word in English has 4 different meanings, and often the sentence doesn't make any sense unless you can figure out the right meaning for each word in the sentence. So there are a lot of combinations that you have to try. A lot of the methods for natural language processing with deep learning or this deep understanding require that you check a lot of combinations out. So often costs and probabilities are involved, and you have to bring in some of the probabilistic reasoning that's so important in AI and other areas. But anyway, so you need to know the exact, you use this deep reasoning when you need to know the exact content of something. So for instance, in legal reasoning, it often makes a lot of difference what exactly it means. My hope is that eventually these deeper methods will eventually surpass shallower methods, because it's not, the languages are not a fixed target. It's true they change a little bit over time, but most of English hasn't changed dramatically from 100 years ago. It's still pretty much the same language. Some words have become more popular and some words have become less popular, but basically it's not a very fast moving target. And so eventually we'll get to the point where we can figure out all the things we need to do deep understanding of language and do that. But right now people are just going through all the details, trying to work out all the details needed for a deep understanding. So here's an example of a parse tree. So if you're going to do deep understanding, you've got to figure out how all the words relate to one another. And usually it uses a classic computer science concept, which is a tree. So you have a tree of all the words, at least the grammatical concepts in the sentence. At the bottom are the actual words that you would use in the sentence. So here would be the parse tree that you use for the sentence, powerboat reported at 30 north and 70 east at 1300, heading east at 20 knots. And so we got concepts like sentence here, and we've got noun group and verb group. Noun group is a noun and all the things that go with it. Verb group is a verb, and then all its modifiers, the things that go after it typically. And in this particular verb group, there's a prepositional phrase with at here. There's another at here for another prepositional phrase, and then there's a third at here. So there are 3 different uses of at here. And there's also a participle here, heading, that's a present participle. And so that's some functions like sort of a fancier form of preposition. And so I've got a participial phrase in here too, as well as the 2 prepositional phrases here and the third one here. And then prepositional phrases typically start with a preposition, and then they have a noun group. And so I put in the noun group. A noun group has different types of things depending on what kind of nouns are involved there. So parsing, by the way, is really important with computer programming, because what typically happens in a computer program is it's put through a parser, a much easier parser than the one you need for human languages. So there's a whole technology of how to parse things that we know about in computer science that you can do to take advantage of this. But again, the problem is there's so many different meanings of words, so many different parse rules. There's often ambiguous sentences that have more than one interpretation or more than one parse tree. And you got to figure out which is the more likely one. So once you got the parse tree, then you got to figure out how the different words relate to one another. And so you need to come up with something like this. Now this is what we call a graph structure in computer science. Graphs are another important data structure that are used quite a lot. And so what this is saying is that this is the powerboat reported at 30 north, 170 east. So there's the main thing in this sentence is a verb here, which I'm going to call are, which is a kind of reporting action. Typically in languages, the most important word in a sentence is the verb. So often you find the verb, start with that, and try to figure out how everything else in the sentence relates to it. So for instance, if there's an important noun, the most important noun in the sentence is usually the subject of the sentence. And so you got to figure that out, and there may be an object of the verb and stuff like that. And then there may be modifiers on the noun, modifiers on the verb. And so that's part of what I'm trying to show here, all the different modifiers. So for instance, this reporting action has a past tense because it ends in ed. We know it's past tense. And it's got a speed here from one of the at things that says speed at 20 knots. And then it's got a direction heading east. It's also got a latitude and longitude, which are also associated with that. And then the subject of the verb is a powerboat. So that's I use the relationship agent here to indicate that there's some sort of be here. The reason I use be and are is that I'm not talking about all powerboats in the world, and I'm not talking about all reporting action in the world. I'm talking about one instance of these things. And I'm just stating for this sentence what the instance is telling me was going on. Anyway, so you've got to get computers to come up with this automatically to do natural language processing. And there's some nice software. People have done a lot of research on it. Of course, there's an area called linguistics, which has been around for a while, which has tried to figure out some of these methods. AI methods are more influenced by computer science, though, and so they don't follow many of the linguistic techniques that people have created. Many linguistic techniques are more for generating language than understanding language. Generating language is also somewhat an AI problem, but it's not near as hard. Usually, if you've got something in the semantic relationship thing like here, there are a lot of different ways that are valid ways to generate English that would describe that. So the hard problem is understanding the language, or natural language understanding. Here's the sort of information that could help with understanding a sentence like that. So for instance, it said something about powerboat, so that's a kind of ship, which is a kind of vehicle, which is a kind of instrumentality, some sort of instrument to do things. And then that's a kind of physical object, which is a kind of thing. And then similarly, there are subtypes of ship, like military ship and fishing boat, and an aircraft carrier would be a kind of military ship. And then we could talk about specific instances of a ship, like Kennedy is a kind of aircraft carrier. And each of these things here on this hierarchy has some information about it. So for instance, ships have a synonym, which is vessel. So if you see that, one of the senses of vessel is equivalent to ship. And generally a ship, by default anyway, should be made of steel these days. And a ship should have a hull, so you'd maybe have some part information about these things. So all this information is called an ontology. So what you need to do natural language understanding for a particular application area is you need an ontology of that area. Now one thing that's happened with online shopping is there are great ontologies now available for products that explain the hierarchy of all the products and all the different properties of products and things like that. And people have been working on developing systems that automatically recommend products for you based on these ontologies. But they're also helpful, and ontologies are also helpful for natural language understanding. And there have been some interesting projects that have tried to build ontologies over the years. Here's an example of another ontology developed at Berkeley up the way here. So this is an ontology information for verbs. And so these are all the, well actually it's also, this one's an ontology for nouns here. It's talking about all the different things that go with money, the concepts that are associated with money. So if you're going to reason about sentences that involve money, this is helpful information. Like for instance, who created the money, who minted the money, what was the purpose of the money, what was it being used for, what material is it made out of, does it have a name like dollar? For instance, where did it come from? How did somebody get a hold of the money? Then there's the possessor, the person who possesses it, the time it was created, the type. So in order to have good semantic knowledge to be able to reason about things, you need common sense information that everybody has learned through their life. And you got to embed that in some sort of a AI format, one of the AI formats that we've probably heard about in the other courses here. So here's an example of trying to do a deeper discourse analysis. Chinese powerboat reported 30 north, 170 east to 1300 heading east, 20 knots, leaking oil. Nearest port is base 83, but is not a full maintenance facility. So there's several things. Once you got the parse trees and once you figured out how the words relate to one another, there's also additional discourse analysis you need to apply to this thing. For instance, you need to know that the powerboat's in trouble. All it said was literally it's leaking oil. You have to know that something about boats and that leaking oil is maybe a bad thing. That's common sense or world knowledge that you need to have. And so if something is leaking oil, you have to know about maintenance on things, that generally requires maintenance pretty soon on a vehicle. And a lot of that applies to a whole class of vehicles, also land vehicles and stuff like that often use oil. And so part of your world knowledge should be to know general principles like this that apply to a lot of vehicles in the world. Also, you'd have to know, for instance, that it must get maintenance at a port too, because they're talking about a maintenance facility. So you have to reason about why the sentence, that second sentence, would mention maintenance. It must have something to do with a need, even though it's never stated exactly what the needs are. So, for instance, if if you've got some leaking oil, you're going to have to get maintenance, and you can only get that at a port. You have to have world knowledge that says you got to go to a port, and so that's why it's mentioning nearest port as base 83. Also, you have to know the leaking oil depletes ship functionality. It needs to be fixed soon. So there's a certain timeliness about this thing. So you have to have some world knowledge that some things are more critical, and the reason they're more critical is there's an ongoing process with leaking oil that's going to make the ship less and less able to do something and get to a port. Okay, so some miscellaneous problems that I haven't mentioned yet. You've got to handle cross-references. So pronouns in English are an example of something that you need to figure out. So if you see the word it, you got to know what it refers to. Usually that means searching backwards through the previous part of the utterance of the sentence to find something that could match the it. And, but it's kind of complicated. You can also have things other than pronouns that are references. So you could say the ship when you mention several ships and you have to figure out which ship you're talking about. Theories of causation. Obviously, one thing caused another thing in many sentences, and like with the ship leaking oil, it's going to cause some problems. So you have to have a lot of knowledge of words-related causation, like because and since and things like that. And it's got to be based, again, on world knowledge of what sort of things cause other things in the real world. You have to know how arguments are constructed. Sometimes writing is intended to persuade someone, and so you have to know oftentimes that when something is in there to help you reach a conclusion or guide you to reaching a conclusion. So you have to have some knowledge of social interactions in order to do that. There's also a whole lot of other social interactions. For instance, how people talk often involves a certain set of predefined communication methods called speech acts, and you have to know something about that. For instance, when in the military, we often model military situations in our natural language processing work. So usually there are orders given, and then somebody that's ordered goes off and does something, and then they come back and give a report. So there's an order action and eventually a report action, which are linked together, and there are various conventional ways in which to accomplish orders and reports. And that happens in the civilian world too, even though they're not called orders and reports. They're sort of similar things there that occur between a boss and subordinates. Then you, of course, as I say, you're going to need to know a lot of specialized situations. There's been a lot of interest in AI in businesses because they have a lot of money to help use AI, and law and politics also have been subject to a lot of of work there. There's a whole area of trying to do legal reasoning with AI that tries to look at decisions and precedents and things like that. And then even though it isn't, there's not as much money involved in it, there's people interested in modeling politics. So for instance, intelligence agencies try to model what's going on in foreign countries like North Korea. One problem now, though, I should point out that if you're going to have speech understanding systems, you have to have a pretty high rate of accuracy. So in the earlier years of AI natural language processing, it was hard to get to 95% accuracy. So people demand at least 99% with speech understanding before they're going to give up and not want to use an AI system. So that's been one of the big things that's happened in the last 10 years or so, is we're getting things much more reliably up to the 99% accuracy rate. Now as far as text understanding goes, you might not need to have 99%. In the early years of AI, people were saying, well, we'll just hire some people to go through the output of an AI translator and check it and then fix anything that's wrong. But it turned out even if there's only a 5% error rate, it takes more time to fix it than it does to you know, just hire a human translator to do it from the beginning. So you have to get up to a pretty high level of accuracy in order for people to apply some applications. So that's been impeding some of the possible applications you might think of for natural language processing. Language generation, as I say, is an easier problem. You still need a grammar and you still need something to say, so you need some semantics to generate what you're going to say, but it's not generally too difficult because with generation you can pick an easy sentence form that, and you can check to make sure it's not confusing to people, and usually it's not too hard to develop some sort of language output from an AI system. Okay, that's about what I had to say. Any questions?